All right, let's dive right in. Today, we're talking about the magic that happens inside your phone with those translation apps. Neural machine translation. We're going to break down the tech that took us from those, well, kind of clunky old translations to the super smooth experience we all have now.
I mean, have you ever stopped to really think about it? You just type something or even say it out loud and boom, almost instantly a pretty much perfect translation pops up. It really does feel like magic, right? But it's not. It's actually the result of this just incredible leap forward in AI.
So what it all boils down to is this. The task is to take a string of words in one language, say it's time for tea in English, and then create a totally new string of words in another, like c'est l'heure du thé in French. And yeah, that might look simple on the surface, but trust me, underneath that simple example is a whole world of complexity that people have been wrestling with for years.
Okay, so where did this modern era of translation really kick off? Well, the story starts with the first huge breakthrough. It was a model with a name that honestly tells you exactly what it does. Sequence-to-sequence, or as everyone calls it, Seq2Seq.
And this all happened back in 2014. A team at Google introduced this model, and wow, it was a total revelation. It didn't just move the goalposts, it completely changed the entire game for machine translation.
So, what is a Seq2Seq model? Well, like I said, the name gives it away. Its whole job, its entire purpose, is to take one sequence, like a sentence in English, and spit out another sequence, like that sentence translated into French. The concept is super simple, but what it can do, that's incredibly powerful.
And this is where it gets really cool. Here's its superpower. You see, unlike the older, more rigid systems, Seq2Seq doesn't care if the input and the output sentences are different lengths. Like how I miss you is 3 words in English, but in Spanish it's te echo de menos, 4 words. That kind of flexibility, it's not just nice to have, it's absolutely crucial for getting translations right.
Okay, so that's the what. We get it. But how? How does it actually pull this off? Let's, pop the hood and take a look at the moving parts inside this Seq2Seq engine.
It's actually a pretty elegant design, split into 2 main jobs. First, you've got the encoder. Think of it as the reader. Its job is to read. Then you've got the decoder. That's the writer. So you have a reader and a writer working together in perfect harmony.
So, the encoder's job, it's to read the entire original sentence, one word at a time, and just absorb its meaning. And then its final goal is to squish all of that meaning down into one single dense package of numbers. It's a vector, and we call it the hidden state. Honestly, the best way to think about it is like a mathematical summary of the sentence's entire essence, a summary of meaning.
And then it's like a handoff. The decoder takes that one summary of meaning vector, that little package of numbers, and uses it as its only clue. It's the starting point to begin writing the new sentence, generating it literally one word at a time in the new language.
Now, to make this whole thing work, there are a couple of clever tricks under the hood. First, there's something called an embedding layer, which is basically a fancy dictionary that turns words into numbers that the computer can actually work with. And then they use these special modules. You'll hear names like LSTMs or GRUs, which are just really good at remembering things over long sentences. They help the model not forget the beginning of the sentence by the time it gets to the end.
But, and there's always a but, right? This brilliant model, as amazing as it was, had one huge critical flaw. A fundamental problem that everyone started calling the information bottleneck.
Yeah, the source material we're looking at puts it perfectly. The model basically ends up throttling itself. I mean, think about it. You're forcing the entire meaning of a long, complicated sentence into one little fixed-sized vector. It's like trying to cram an entire encyclopedia into a single shoebox. It's just not going to fit. You're going to lose stuff.
So, that's the heart of the problem, right there. That summary of meaning vector. It becomes a bottleneck. The longer the sentence you feed into it, the more detail and nuance and important context just gets lost in that compression. The model literally starts to forget what it read at the start of a long paragraph by the time it's supposed to translate the end. And you can see the real-world result right here. I mean, look at this. For short sentences, performance is fantastic. But as the sentences get longer, the quality of the translation just falls off a cliff. It was a massive problem, and it desperately needed a solution.
So the big question was, how do you solve this bottleneck? Well, the solution that researchers came up with was not just elegant, it was powerful. And it has a seriously cool name. Attention. The whole breakthrough really came from asking one simple but brilliant question. What if, instead of forcing the encoder to cram everything into that one tiny vector, what if we just let the decoder look back at the entire original sentence whenever it wanted at every single step? And that changes everything. The whole dynamic just flips. The old way was like giving the decoder one summary and basically saying, here you go, good luck. But this new way, this lets the decoder actively focus on the most important words from the input, for the specific word it's trying to write in that exact moment.
So, at its core, that's what the attention mechanism is. It gives the model a skill that feels, well, it feels very human. It's the ability to pay attention to the right thing at the right time.
Okay, let's make this concrete. When the decoder is about to write the French word l'heure, the attention mechanism lets it look back at the English sentence and put a huge spotlight directly on the word time. And the amazing part is, it learns to make these connections all on its own.
So, there you have it. Attention was the fix. It didn't just solve the information bottleneck, it completely smashed it. All of a sudden, these models could handle really long sentences, and the translation accuracy just went through the roof. It was another revolution because it was a total shift in how we thought about the problem, from forcing a model to memorize to letting it dynamically focus. This idea was an absolute game changer. When you boil it all down, attention is all about focus. It gives the model the freedom to decide for itself which words from the original sentence matter most for the word it's writing right now. And that's what leads to translations that are so much more accurate and aware of the context. And that really leads us to a fascinating final thought. Because this whole idea of attention, it didn't just stop with language translation. Think about it. If a machine can learn to pay attention to the right words in a sentence, well, what else could it learn to focus on? The most important pixels in a photograph? The key notes in a melody? That very question is what kicked off the next massive wave of innovation in AI.